Hello, I am Ohad from Apollo 9662, and I will be introducing Inventor simulations. First is the stress analysis simulation. You begin by pressing Create Study. Then find fin bodies, and ideally you would press a button and it says no. Then you assign material. I already did. You can see at the top aluminum 6061. Then the constraints. Fixed is for any place that is fixed, bolted in place. So that's what I'm doing in the video. You can see every place that has a place for a bolt, or even a bearing, because those are also connection points, I fix it. Pin is essentially for things that can spin in place but not move along their own axis. And frictionless is for things that can move along a plane but can't move outside of that plane. So you can see in this, so you can see here, I have various constraints. Now I missed a few holes, so I am just going to patch these up. And I will now apply loads once I finish messing around with the constraints. You apply a load of whatever you want, measured in Newton or pound force. I usually go with 1000 Newton. Pressure is the same as force, essentially, except it's always normal to the face if it has a curve, whereas a force would curve with the face. So that is the difference. Force usually isn't used. Bearing forces are for, well, bearings. It's the force that goes on, that happens when you place a bearing in place and it spins. So that area is applied with a bearing load. Now, gravity is, well, gravity, but you gotta make sure that it's applied in the right direction. You can see it in the arrow. So you can see I applied all the forces. I applied here a force of 1000, I believe a bearing of 500, and 1g of gravity. These are my normal settings. Usually if a part can pass 1000 newtons without being hurt, then I can send it to manufacturing, because a normal robot won't really apply 1000 newtons. So that's what I recommend. Now you can simulate, and this takes a little while. And you can see that the part that is bent is the part that is the weakest. So that central bearing hole and that edge, neither of these have any fixed points, so nothing to hold them from bending, and they have weak areas. Basically, blue is good, red is bad, green is okay. If a part is green or worse, you should replace it with, or make it harder and less bendable, because a green or worse can be bended by hand, which is not what you want. So you can see the various types. You can see how it changes the result. You can see how here in displacement, that's a useful one. You can see exactly which parts are the most displaced and which parts need the most strengthening. That's a very useful one. And safety factor is just a harsh version that shows every possibly weak place in the entire part. It is a safety factor. If a part, you don't really need to pass the safety factor because it's extremely harsh. It's made for industrial scale parts, but it is a useful thing to look at. Now next, I will show you how to do a sketch analysis. A sketch analysis is it's pretty complicated, it's pretty hard to do properly, but if you do it properly, it can save you huge amounts of time. I always make sure to do that to any of my systems. Now this one might not be a simulation. Inventor doesn't do it for you, per se. You can see, once I zoom in, you can see I have a full sketch of what my robot will look like. That was an early sketch of our robot. You can see I have the motors and motor holders, and our pivot slides, and the motor that powers it, the slides themselves, and the odometry pod. These yellow circles are the wheels. All of this is accurately sized. Now these are actually blocks, meaning these are lots of lines and parts and sketch parts that I combined into one. So you can see you have that is pretty close, but because we did a sketch analysis, we knew it would be fine. Were we to actually build it, which we did, and it was fine. This is a pretty accurate method of seeing what's okay and what isn't. Now this is going to be an aerial view from the top, and the blue parts that are at a weird angle, you can ignore those. They are an experiment that failed. You can see I have the motor holders and the odometry pods, and the motor that the white part is the motor for the pivot slides, the wheels, and the blue parts are the plates of our chassis. And you can see that this is essentially a, a non. This is 2D versions of our robots from different angles. So this is a powerful tool. You can see I used color coding to basically say something is on different heights. So even though the odometry pod is and the holder are on the same place, you can see because in the aerial view, the motor holder was green, that meant it was on a different scale. And you can see this even shows how the robot will work. You can see I can mess around with the dimensions and extend our slides and change the pivot. It's overall just a really useful tool. Now we'll go into the shape generator. So I'll remove all of our pocketing, and you can see I already did a little bit of this. That was from a different study. Now, as per usual, you'll create a study. and assign material and add fixed points. That's all well and good. Exactly the same as in the stress analysis. So I'll do that real quick. Now I won't run the simulation fully because this one takes a pretty large amount of time. Now, one key difference here is that the fixed areas in this aren't actually any place that is bolted into place. It's any part that has anything connected to it. So I applied the fixed constraint to all of my different holes. Now I'll apply a force, the same force, 1000 newtons, and preserve region. This is the important one. You basically create these green areas and tell it to not change those areas. Because the shape generator is essentially a guide for pocketing. Now you have your symmetry planes, you can see. I can decide where I want it to be symmetry. And I believe so. We went over preserve region and fixes. So a really important note. This is the one thing. This thing does not pocket for you. It is a useful guideline for pocketing, but if you were to just trust that it did it okay, it did not do it okay. Because one thing that it can't understand is how struts work. So unless you tell it where to place struts, it will not place them, and by that point you would already have pocketed the part, so there is no need. Now the actual calculating does take a little bit. It takes a while to actually calculate everything, but we'll see soon enough that part of that it will turn into a mesh. Here we go. And you can see everything that it kept and everything that it got rid of, and all the areas I told it to keep are kept. And you can see that here, we can see it kept the bare minimum of what I told it to. And here we can see that this is like a weak area, so it needs extra strength. So you shouldn't remove much material from that area. Whereas the areas that it emptied out are stronger areas, more resilient, so you can be more aggressive with your pocketing in those areas. So this serves as a nice guideline. You can see here this place, this tiny little place, is a place that you can take a little bit off. Again, this is for industrial grade stuff. And you can promote shape, which gives you this yellow thing. And basically wherever it's yellow is the weak places, and where it is not yellow is the strong places where you can be aggressive. And you can see it shows that little corner that's bended in the stress simulation, and that bearing that also bended, you can see that it depicts those as the weak places. So this is in line with what we saw at the stress simulation. Sorry for that. So, I believe that is all. I'm, there are other simulations in Inventor that aren't exactly the best, but here, for example, a dynamic simulation. It is a simulation that is very useful before you build a robot, but it is incredibly complex, unimaginably hard to do. But if you can do it, I might make another video on that if I ever manage to get it to work. If you can do that, it's an amazing resource. Good luck!